My name is Aaron Weiser, and I'll be going over the water level system for the proportional only controller experiment. My teammates are Addis Jakubovic, Drew Pace, Ashby Ward, which is not here at the moment, and Becca Palmer. This is the outline of what I'm going to be going over. The background of our system is a schematic of the system itself, the SSOC calculations and the graphs, the step response calculations, results in the models, the sinusoidal and relay input experiment, the root locus experiment, and the focus of today would be the proportional only controller experiment, and I'll be going over conclusions.
Go straight to sinusoidal.
Sinusoidal. This is an example using the frequency of 0.002, and it's in the range of 6 to 8 centimeters. That's just really an example. This is how we got our change in input and the change in output, and the period and the tau. This slide shows the 0.004 was the highest frequency we could go with without our output becoming a straight line. So you'll see in a few slides what that means to us. Yeah. But we could get basically 4 data points before it started becoming linear. This shows the 4 points, and like most other graphs, ours does not go to the 180 mark or to the 0.1. So the KCU and the FU for the Bodie was not found with our system. And this shows if it did. This is projected merely just to show if it happened to. It's a guess more than anything, so it really doesn't mean very much. This is to show that where the points for the model for the frequency and amplitude ratio, the blue dots, and then the experimental is the green dots, and the purple line is the co-fit for that. On that one is the frequency versus phase angle and semi-log plot, and also the blue dots are the model, and the green dots are the experimental values, which matches up fairly close. These are the equations of the phase angle and amplitude ratio. They was used to get the K, T naught, and the tau for the 4 to 6 centimeter range, 6 to 8 centimeter range, and 8 to 10 centimeter range. And also, I noted where the KCU and the FU values cannot be calculated from the Bodie plots because we couldn't go over the frequency of 0.004 for the relay. The relay was observing time responses of output function for set values of the motor input, and was able to find the KCU values and the FU values. And me and Becca was able to do the relay experiment. This is the actual relay experiment that I ran. I'm showing this because this was done when the test system was gathering information one data point every 2 seconds, which was not enough. So I was coming up with graphs like that. And with graphs like that, it's nothing that was able to come from it. But this is Becca's, which was the data points was increased to, I think, 2 or 3 per second, and was able to get a more linear graph. And also, I want to note that I think Josh Solomon, he had a question about why that did not change whenever we changed the ceiling. So I was going to get back to you on that. Our system stops at 39%. It doesn't really stop. It quits producing water because of the friction in the pipes and the and the vertical more the head of our system. And so that's why it never changes, because at 20 it's just the same thing as 39. This was, we was able to calculate the relay parameters for the KCU. It's over four times the change in input over 5 times the change in output, and the ultimate frequency was 1 over the period. And this was a sample of how we was able to get the period from one point to the exact same point on the different amplitude, and the change in output, also with the change in input. Now this is our KCU and FU values that was obtained from the relay experiment. We have 14% over centimeters for KCU and 0.02 hertz for FU. Following two graphs are comparing the K, the dead time, and the tau, or time constant, for 3 different procedures or experiments. The K value is averaged around 0.8, which is consistent with the model, the sign, and the FOPDT step experiment. And I put P0 and tau on the same graph because they're both seconds. You can see that the dead time is right around 15, and tau, it's between around 80 to 90 seconds, with the sign being the most, being the greatest, which we're not really seeing why that's as high as it is. Comparison to the variance between FOPDT and the sign is high for tau, and the uncertainty for the sign experiment was high compared to the others. Group locus modeling. The first equation was the transfer function for the FOPDT for our system, and substituting Pottay's approximation, it becomes the open loop transfer function, the plot equation. This is an example of the root locus plot for the ranges of 6 to 8 centimeters. This has the decay ratios on there. We have the at a 45-degree angle, which is the 1/500th. The decay or controller gain is 3.5% per centimeter, and then the 70 degree is the 1/10 controller gain at the 7.2% per centimeter, and the 78 degrees is quarter decay, quarter controller gain, which is 10% per centimeter, and then the ultimate controller gain is 15. And then we have an overdamped region right here, and then the underdamped region is up there. The KCU comparison between the root locus and the relay matches up fairly good, roughly around 14.5% per centimeter. Root locus KC values. The customer should choose a controller within these ranges for the ultimate controller, 15 to 17% per centimeter. For the quarter controller gain, 10 to 11% per centimeter. 1/10, 7.2 to 8.4% per centimeter. For 1/500, 3.5 and 4. And the critical decay is from 1.9 to 2.2% per centimeter. And this is our newer experiments that we just done. First, I think 8 slides is for the 2 to 4 centimeter range. Then I'll get with the other. I'll talk about the other teammates. This is for a critical decay of 2.2%. It was predicted from the root locus, and you can see it was very stable at the beginning, and when it stepped up, it was stable throughout the rest of the experiment. It had an offset of 0.45, and that was achieved by the output did not match up with the set point, so we had to bring that down, and when you did, that lowered that below the set point, so it is at 0.45 with a decay ratio of 0. This is using a KC of 4%, which is predicted from of 1/500 from the root locus, and it had an offset of 0.3 centimeters, and it still had a decay ratio of 0. This is the using a KC, and this was done after the fact where I found my ultimate. And so I was curious, so I started doing more experiments, and this was just 6% for controller gain, and I was still getting a stable response throughout the whole entire experiment with an offset of 0.45, but I was getting a decay ratio of 1. This is another, for curiosity's sake, with using a KC of 7%, and I was getting a offset of 0.05 centimeters and a decay ratio of 0.9. This is using KC of 8%. I'll come back to that in a second. This was 8.4, which was the 1/10 decay of what the root locus predicted, or what the root locus said would be the 1/10 decay. But upon doing this in the proportional controller experiment, I was coming up with this would be my ultimate. So I was thinking I did not have to go any further, any higher with the KC values. And so that's when I decided to go back and see actually where I would find it. And that's when I started doing the 6, 7, and 8%. And I was getting a little decay ratio there, so I knew it was 8.4 was probably my ultimate controller gain. And then, for curiosity's sake, I did 11% because the ultimate controller gain that the root locus had said was 15, I think, 15% per centimeter, and so I decided just to go on up, and I was getting oscillation here at the beginning, and when I stepped it up, it becomes stable. So at this point, we do not know why it's doing this. And then I did 17%, it wasn't 10%, per centimeter for the predicted ultimate, and I was getting oscillation at the beginning, and then it was become stable, and then it started oscillating again. And again, I do not know why it was doing this. And I guess instead of a decay ratio on this, it would probably be more of a growth ratio. And this is an experiment done by Otis for the 4 to 6 centimeter range. It was the predicted 1/500th decay, and he used a KC of 5.5%, and it was stable throughout the entire experiment with an offset of 0.3 centimeters and a decay ratio of 0.2. And this was done for his predicted ultimate, which was oscillation. It had oscillation at first, and then after the step, and then it becomes stable. So this follows what his ultimate pretty much would be, with an offset of 0 and a decay ratio of 1. This is an experiment run by Becca. She did it between the 10 and 12 centimeter range using a critical decay rate, decay controller gain of 1.9%, and you can see how it did not match up with the set point. So if you bring that down, it would be an offset of 0.5 centimeters, and it had no decay ratio on that either. This is another one she did for 15%. It had a step down from 11 to 10 centimeters, and her input was 54%. And then I want to compare between a KC of 4% with a step of 1.25 centimeters, and then a step of 5.5 centimeters. This is a graph that you had already seen, but you can see I stepped from 2.5 to 3.75 centimeters, and then it was stable throughout with the predicted 1/500th decay. And then the next slide is where I stepped up 5.5 centimeters up to 8 centimeters, into another teammate's region, and you can see that the overshoot was definitely there, but it was stable throughout, so that matched up with the other one. These are table of all my data point or data that I've gotten. This is the KC values. This is for the step up with the 4% KC with a step of 5.5 centimeters. That's why it's different. That's why it's way down here. And you can tell that I had the monotonic and then the oscillation, and then this one is one where it was stable at the step and then it started oscillating again. And I want to draw your attention to the different ways of figuring out the offset. These, you can do it experimentally like with a proportional controller. You can do it graphically where you're drawing actually the lines on the SSOC graph and offsetting the lines up and getting it that way and measuring it, or you can use the formula, which is the 1 minus KCK over 1 plus KCK. And you can tell from the table here that most of them match up fairly closely. And for the conclusions, the KCU for the 2 to 4 centimeter range was the ultimate controller gain for the 2 to 4 centimeter range was 8% instead of 17 that was predicted in the locus. And then some K values caused really strange behavior within our system. And also the proportion controller was another way to find the offset. Any questions?